Hello, my name is Andy Schweitzer, and this is a little short video on kinetics of a chemical reaction. Just so you're aware, the term kinetics, I'm just going to grab my pencil here, and the term kinetic means referring to the rate of a reaction. And in the end, it's eventually going to want to, and we're not going to get that deep into it, you're going to want to be able to predict how fast a reaction is going to run, and then in the end you'd even want to be able to predict why, or try and figure out why this thing is working the way it is. But for us, we're really just going to look at the very surface of this thing, and our main objective is to look at the factors that might either affect the rate now. We usually deal with this topic in honors chemistry, or general possibly even in the end of a reactions chapter. We now know that there are chemicals. These chemicals undergo chemical reactions. We learned all different types of them. Now we hopefully learn that a reaction, let's say A plus B yielding C, this reaction is going to proceed at some rate. Okay. Now you can speed that rate up, slow it down. We can do things with it. Before we get into that too much, we're going to look at what's called the collision theory. What do we need actually to have a chemical reaction? Now, if I want to have A plus B proceed to C, what do I have to have in order for this reaction to occur? Well, the thing called the collision theory states basically that, one, the two particles have to simply collide with some amount of force, okay? And two, there needs to be some kind of geometry that these things need to hit with. So for example, let's just say hypothetically that I could be this A could be simply a protein, or it could be an element of some sort of molecule. I'm just being very generic about this. And and this is what I mean by generic. Let's say A looks like this, okay? Now, this might be the sensitive location for which that a reaction can occur. And let's just say hypothetically that B looks like this, okay? And this little part here is the part where it is also sensitive. So these two things literally need to collide in this direction to create a situation like this, where this is A, and then B might look something like this, like that, okay? And then from there, it's going to produce maybe a new compound, which we're going to call C. This is an intermediate point, which we would call the activated complex. Now, the question might be at this point is, okay, what does this mean for us to increase the rate of a chemical reaction? Let me give myself a little more room here. So, in this sense, a few things have to happen here. One, they need to collide at a certain geometry and with a certain amount of force. So everything that we are looking at for increasing the rate of the chemical reactions is inherently going to increase the number of collisions. It is possible to have a collision that's not successful. Even if they collide in the right orientation, it still may not be successful if you don't have the right amount of force. Now, as these particles are flying around inside of a container, let's say we have a mock container here, and A and B, let's say they're gases, or they could even be liquids, it doesn't matter. A and B are simply flying around, and dots represent both A and B, and they're flying around at pretty good velocities, moving around, bouncing off walls, bouncing off of container or whatever other particles, and they randomly collide. To my knowledge, I don't know, unless we have an actual enzyme that can take A and place it inside of B, then we really can't control how a rotating and spinning and transversely and translationally, essentially A and B are going to bump into each other, and we can't control how they hit each other. So it's just a matter of chance that A hits B correctly. And there's a certain fraction of the collisions would be in the right orientation. What we can do is increase the total number of collisions, and therefore having more collisions, that same fraction is a larger piece of the pie to get effective collisions in the right orientation. So we can't really control the geometry at this point. All we can do is increase the number of collisions, and having more collisions, then have a larger amount of those collisions. So let's say 10% of the collisions are good. Then having more collisions means 10% is a larger number. Okay, so that hopefully is well understood. But either way, everything else we'll look at will be how to increase the number of collisions. We watch a little video on this usually in class, and it is, for the most part, it is a very good video, and it has a lot of factors involving here. Okay, and I'm just going to walk through them quickly here, and that would be pretty much it. Okay. Number one is simply going to be concentration. Okay, if you increase the concentration of A and B for a given volume, okay, concentration is an area, stuff per area. This is going to give you more particles, and therefore they're moving, and therefore more collisions. It's like putting a bunch of people in a room. As they're moving around, they bump into each other. You get more people, they're going to bump into each other more. The next one is going to be temperature. As far as temperature is concerned, that means they're moving faster. So even the same number of particles, if we warm this container up, these particles are moving faster and faster and faster and faster, and eventually they will hit each other at a greater frequency. So temperature is unique. It will increase the number of collisions, but it will actually increase the force of collisions. Let's squeeze it in there. What you want to be aware of is that temperature, and temperature kind of fooled people, mankind, for a long time. Temperature is essentially the actual chemical name for it is average kinetic energy. Kinetic means movement. Okay, and it increases the movement of particles. Temperature is movement of particles. So when you have a particle, force equals mass times acceleration. The faster it's moving, the larger force it has, the more momentum it has, the more impact it has. So when A and B actually collide, if they're moving at higher temperatures, they hit harder because they have more speed, more we call molecular velocity. Now, other things that we might be able to add on here would be one, surface area. This is a pretty good example of, we might say, a grain elevator. Okay, you have basically, let's say, a big building or a mine, in which case, let's just say we have a building, and it's storing grain or stores anything that can potentially be dusty. And metals, we don't think of being very flammable, but they are extremely flammable. So if we get gases that have lots of stuff in them, very high concentrations can cause all sorts of explosions, and this does happen in industry. Another example might simply be the evaporation of water. I can literally take a beaker, test tube, let's say, of water, okay, and some water there, and I could leave it there the very first day of class, okay, and go all the way to the last day of class, and that test tube of water will be pretty much exactly the same. Yet I can take that same test tube with another one, day one, and pour it out on the floor, and it will be gone within minutes, before the classroom is done. So surface area is an opportunity for something to take place. Just like in a grain elevator explosion, we have larger concentration of gases, particles. Therefore, more particles means more collisions, which means more reactions. Surface area. Another big one, would be a catalyst. Okay. Now, a catalyst is kind of easy to think about, but harder to really truly understand. You maybe not know enough to really understand how it works. But one or two things you might want to know about catalyst is, one, it cannot make an impossible reaction possible. Okay, and next, it is not consumed in a reaction. So it's there in the beginning and it's there in the end. So if I were to have, let's say, A plus B yields C, it would be in the reactants and it would be in the product. So technically, it would get anything that's in the same on both sides gets eliminated. So we generally write it above the top here. You might put a catalyst in, let's say, MnO2. You can't see that real well. Magnesium dioxide is a kind of a common catalyst, or platinum, or we'll list it above the yield sign. Now, the question is, how does a catalyst work? Well, a catalyst, and a common biological catalyst would be called an enzyme, but a standard catalyst uses what's called a different, or it sets up a different reaction mechanism, which means it literally takes a different pathway to get it to collide, or to get it to chemically react. So before, where we had A and B, where we had them simply A and B, okay, where they literally would need to collide to produce C, this may use some other chemical or some other entity, let's just say E, and E might have some means of bringing, A reacts with E, which then facilitates B coming in here, okay, and then they eventually walk away, and A and B are together, and E is now again all by itself. So it's a series of events, and it's not the same collisions that we had originally. This would be the original means, and this is a new method of what they get put together. Sometimes we use a human example where person A and person B want to, let's say, meet and form a relationship. And it could be something that is like a boyfriend-girlfriend, or it could just be friends, okay? A and B might never end up being friends. But all of a sudden, you have person C, okay? And person C knows person A, and then they might know person B, and then now A and B now know each other. So, and then, of course, these two might be very good friends, but now C is out. C is not there anymore. So C is a catalyst by which these two people met each other, okay? If A and B have two unique personalities that would clash, C cannot make them like each other, okay? It simply can speed up. All it does is simply speed up something that would could or already happen on its own, okay? It uses a different means by which bringing these people together. So that's a humanistic example. But again, it all comes down to the collision theory of two particles colliding. Thank you very much.